Hey guys, in this video, I'm actually going to show you that the limit as x approaches 0 of sine x over x is actually 1. Okay, and I'm going to use a geometrical figure to show you why. All right, so let's check this out. Do you guys all agree that the area of this yellow triangle that I inscribed in yellow is smaller than the area of this sector, which I have in orange? Yes, right? You guys notice that the area of the sector of the circle is more than just that yellow. And do you guys also agree that this triangle has the most area? Of course. So, with that being said, if you take a look at what I wrote here, I'm going to show that the area of AOC is less than the area of the sector of the circle AOB, which is less than the area of the triangle AOD. So, if you guys recall from Algebra 2 or from pre-calculus, the area of a triangle is always 1/2 AB sine C. Now, some of you might say, isn't it 1/2 base times height? Yeah, I mean, that's what it reduces to if you have a 90-degree angle because the sine of 90 is 1. But if you ever want to make sure that you can find the area of any triangle, whether it's a right triangle or one that has, 60, 60, 60 or 30, 60, 90 or whatever it might be, you always just use this area. Now, A, B, and C are just arbitrary letters. So I want you guys just to remind yourself that the area of a triangle is any two sides as long as you have the angle in between them. So you take 1/2 any two sides as long as you have the angle in between them. So let's take a look at AOC. AOC is this guy right here, okay? I have this, I'm going to say that this is in a unit circle. So that's 1 for that radius. I'm also going to say that the radius from here to here is going to be 1. I think I drew this should be coming straight down. So, okay. So the area of AOC is going to be 1/2 1 times 1 times sine of x. Okay, so that's the angle in between them. So we have 1/2 sine x. The area of the sector, I don't know if you guys remember this formula, the area of a sector, I'm going to write it up here, is 1/2 r squared theta. Okay, and there's some, I'm sure you can look up a quick proof of why that's the area, but just take it for what it is. R in this case is the radius, which is 1. Theta is an angle, in this case it's x. So I have 1/2 1 squared times x. So in this case I have just x over 2. The triangle AOD, which is going to be this big guy, I'm just going to highlight all of it. Well, once again, the area of a triangle is 1/2 AB sine C. So I know that when, I hope everybody remembers the circle theorem, but basically when you have a radius, which I'm highlighting right here in orange, when you have a radius that meets a tangent line, in other words, it meets at exactly 1 point, then at that point, there forms a 90-degree angle. Okay, so you would have to remind yourself of that theorem. If you have a radius and a tangent, you see how this only hits 1? It creates a 90-degree angle. So, I said earlier that the area of a triangle is any two sides, I'm highlighting this one here, times the sine of the angle in between them. I have this angle here. So right now I have this to be, let me go back to black here, 1/2. I have one side. I'm looking for this other side. I'll just call him B right now, times sine of the angle in between, which is 90. So how do we get this side right here? How do I get this side right here? Well, I can just use SOHCAHTOA. So what I'm going to do is I'm going to locate this angle x here, which I have right here, and I'm going to say that's going to be opposite over adjacent. So I'm going to say that tan of x is equal to side AD, which I'll just call B from now on, side AD, which is opposite, over adjacent, which is 1. So what is B? B is actually tan x. So I'm just going to substitute the B right there. And this is going to reduce to 1/2 times 1, which is 1/2, times B, which is tan x, times sine of 90. You guys have to know that in sine of 90 degrees is 1 as well. So currently, I have this here. You guys notice what they have in common? A 2 in the denominator. You can throw all of that away, or basically times the entire expression by 2. So you're left with sine x is less than x, which is less than tan x. But I'm going to rewrite tan x as, let me get rid of this little black part here. I'm going to rewrite tan x as sine x over cosine x. So now what I'm going to do is I'm going to divide everybody by sine x. I'm trying to squeeze this thing, okay? So right now I have sine x. I'm going to have to add a new page, sorry. I have sine x is less than x, which is less than sine x over cosine x. I'm going to divide everybody by sine x, so that's going to be 1 is less than x over sine x, which is less than 1 over cosine x. Okay, you can also flip fractions as long as they are monomials, okay? And these are all single terms, so I'm going to flip all of them. So when I flip them, I'm going to just go like this. Okay. What would happen if I take the limit as x approaches 0 for all 3 of these pieces? Well, that's just going to give me 1, right? Because there's really no place to substitute your x in, right? If you try to do some direct substitution. I don't know about this guy here. I'm trying to basically solve for him. And what's the limit as x approaches 0 for cosine x? Well, you guys remember that cosine x is a continuous function. The limit as x approaches 0 for cosine x is also 1. What we noticed here in this problem is that sine x over x is right between 1 and cosine x. And basically, if this guy right here goes to 1 and this guy right here goes to 1, then this guy right here gets squeezed into going to 1 as well. So therefore, the limit as x approaches 0 of sine x over x is 1. So I hope that was helpful. And in the next video, I'm going to just apply this with another trig identity limit thingy. All right, come back for that one.